Hello there, welcome to AP Calculus, section 5.5, lecture 1. In the book today, we're going to be on page 354. And what I'm going to be teaching you how to do is take derivatives of logarithmic bases other than e. So in the last section, 5.1 through 5.4, we took a lot of derivatives with bases of natural logs, all right? We took derivatives of natural logs. And today, we are going to take derivatives of logs that don't have a base of e, so not the natural log. So just a quick review of logs. Just remember that a log is an exponent. So we're going to go over a few examples from the text to remind you how to convert logarithmic expressions to exponential expressions and vice versa. So let's look at number 2 on page 354, where we are given that log base 27 of 9, and we want to convert that to an exponential expression. So a log is an exponent. So that means this entire expression is just another way of writing an exponent. All right, so the base is 27. The exponent is what we're trying to solve for when we evaluate this logarithmic expression, and we set that equal to 9. So hopefully you can do this in your head. 27 to what power is equal to 9? Well, x would be equal to 2/3. Of course, you could check that in your calculator. But that is the evaluating this logarithmic expression, and it gives us the exponent. So just to double check that, we could rewrite this as a radical. Remember, the denominator of the radical goes into the denominator of the fraction goes into the crook of the radical, and then the numerator is what we raise the power to underneath the radical. Okay, so the cube root of 27 is 3. So this is 3 squared, right? 3 cube root of 27. Let's do that first, and then square it. 3 squared is 9, and that matches right here. All right, let's take a look at example 6. Still on page 354. So part A, we want to take 27 to the 2/3 is equal to 9 and rewrite that as a logarithmic expression. Of course, we just did that. We know the answer. All right, but the base is 27 because that's what the exponent is connected to. So this is going to be log base 27 of 9, and the number that's by itself with the equal sign is the exponent, 2/3, because that's the answer. Remember, a log is an exponent. All right, part B, we have 16 to the 3/4 is equal to 8. So that's like taking log base 16, 16 is the base, of 8 is equal to the exponent 3/4. So it's just a rearrangement of this exponential expression in terms of logarithms. All right, let's take a look at number 8. Okay, for that, part A says log base 3 of 1/9 equals -2. So we want to rewrite this as an exponential expression. The base is 3. The exponent is -2. Remember, it's by itself with the equal sign, so is equal to 1/9. Remember, negative exponents, this is the same as 1 over 3 squared, right? You can put a 1 over that expression and change the sign of the exponent. So 1 over 3 squared, we know that's 1/9. Part B, we have 49 to the 1/2 is equal to 7. We want to rewrite that as a logarithmic expression. So the base is 49. So that's log base 49 of 7 is equal to the exponent. All right, so remember, a log is an exponent. So this is the logarithmic version of this exponential expression. All right, we've got a few more to do here. And then we'll get into taking derivatives. Let's look at example 10. We're just going to do part A. And that one says we're going to evaluate, get the answer for x. It says we have log base 4 of 1 over 64 is equal to x. All right, we want to rewrite this as a logarithmic expression. So that's going to be the base 4 to the exponent x is equal to 1 over 64. So we know that 4 cubed is 64, so 1 over 64, the exponent would be -3. So 4 to the -3 is equal to 1 over 4 cubed, which would be 1 over 64. Okay, let's look at 12a. So in that one, we have log base b of 27 is equal to 3. So let's rewrite this as an exponential. That's going to be b, the base, to the exponent 3 is equal to 27. And hopefully you can do that in your head with no trouble. B is going to be 3. And then our last of the logarithmic review, because when we do derivatives, we're going to have to rewrite these, but the last logarithmic review we'll do 14a. And in this one, we have log base 3 of x plus log base 3 of x minus 2 is equal to 1. So what you want to do is use the properties of logs to rewrite this expression as a single log. So I would have log base 3 of x. Now when you have addition, remember it's multiplication. So x times x minus 2 is equal to 1. Now we're going to rewrite this as an exponential expression. So I'd have the base 3 to the first power is equal to x times x minus 2. So 3 to the first power is 3. I'm going to go ahead and distribute the x, so I'd have x squared minus 2x. Okay, let's bring that over here, give ourselves a little more room. I'm going to set this equal to 0, so I'm going to pull that 3 over to the other side. I would have 0 is equal to x squared minus 2x minus 3. We can answer this by factoring. So I'd have x, and then how about minus 3 plus 1? If we FOIL that back out, I'd have x squared minus 3x plus x. That'd give me minus 2x, and then negative 3 times 1 is negative 3. And then I'll set each side, each parenthesis equal to 0. So we'd have our answers x is equal to 3, and what makes this expression 0 would be negative 1. Now you can have extraneous answers, and if we plug these numbers in, if you plug -1 in for x, here you will have, you're taking the log of a negative number, which you cannot do. So -1 is extraneous. Because you can't take the log of a negative number. So you got to be careful for this kind of problem on the test. Make sure you're not giving an extraneous solution. All right. So now let's get into derivatives of bases other than e. So the question that we want to answer is, what is the derivative of y equals log base b of x? So what we want to do, our technique is to rewrite in terms of natural log, because we know how to take derivatives of natural log. We just did that in the last section, using the change of base formula. Okay, so remember the change of base formula. We're going to rewrite this expression, and that's going to be y is equal to, remember, the b goes in the basement. We're going to do it in terms of natural log. So we would have natural log of x over natural log of b. Well, the natural log of b is just a constant. So what you want to do is bring that constant out front. So we would have y is equal to 1 over the natural log of b, because it's on bottom, times the natural log of x. That's just, we rewrote it that way just to visualize it a little better. Now I can take the derivative, y prime, the constant just stays there, just stays right out front. Remember, the derivative of, if y is 3x, y prime is just 3, right? So the constant stays out front, and then we use our derivative rules for natural logs, which is going to be 1 over x times the derivative of x. So times 1 over x, and the derivative of x then, what we called the blop, the derivative of the blop is just 1, right? So the answer then, and we're going to want to put x out front here. So that's 1 over x times natural log of b. We bring it out front so that we know, we can show that it's not the natural log of b times x, okay? You're not taking the natural log of x, so let's bring it out front there. So that's really the basic formula, and we have to, when we get fancier examples, we'll do an example, a simple example first. So let's find y prime if y is equal to log base 5 of x. So first we're going to rewrite using the change of base rule. That's going to be the natural log, let me say y equals, the natural log of x, right? The x goes on top, and then the b, then you have the base in the basement over the natural log of 5. And we're going to pull that 1 over natural log 5 out front times the natural log of x. So this is our constant, 1 over natural log 5. See that? that and that exactly the same. So y prime is going to be equal to, just write the constant, 1 over natural log 5 times the derivative of the natural log of x, which is 1 over x. And then we're going to clean that up by rewriting it as 1 over x times the natural log of 5. So that's the most basic type of problem that you could get in your homework. But we're not going to stay with the basic, are we? We're going to have to use the properties of logarithms to rewrite and maybe do some chain rules and things like that. So building on what we did last section. Okay, so let's do another example, a little fancier one. Let's find the derivative. This time we'll write it as d over 8 dx. So take the derivative with respect to x of y is equal to log base 3 of sine squared x. Okay, so first let's rewrite this. We want to rewrite it to our advantage. We're going to use this change of base formula. So we're not at y prime yet, we're just y. And it's the natural log of sine squared x over the natural log of 3. Now I'm going to continue to rewrite to make my life a little easier here. Well, let's bring this natural log of 3 out front. 1 over natural log 3 times the natural log of sine squared x. So y is equal to that. Well, I can still do a little more here maybe to help me take the derivative. 1 over natural log 3 times the natural log of sine x all squared. So sine squared x, another way to write that is sine x all squared. So this makes our life just a little bit easier to visualize, because what I've been calling the BLOP or the inner function, we have the sine squared x, and then we have an even more inner function, which I'll show in green, sine x. Okay, so we have a chain rule here. So y prime is equal to 1 over natural log 3. Now, first of all, it's 1 over the entire expression. So the derivative of natural log of sine x all squared is going to be 1 over sine x all squared times the derivative of sine x all squared. So that's 2 sine x. So bring the 2 out front, 2 times sine x to the first power. Okay, so I'm not going to write the 1. And then what's the derivative of what's in green? The derivative of sine x is cosine x. Okay, so we've got a chain rule here. 1 over the entire BLOP, sine x squared, and then derivative of sine x all squared would be 2 times sine x to the first power times the derivative of the innermost, or what I've shown as green's derivative of sine is cosine. Now we can simplify some. One of these signs goes away. And so we can rewrite this as 2. The 2 I can bring out front as a constant. 2 over natural log 3 times cosine x over sine x. So we still have that sine x on bottom. Brought this. Well, like we can do even a little better here. We've got 2 over natural log 3. What's cosine over sine? Well, sine over cosine is tangent, so cosine over sine would be cotangent. So pretty cool. And that would be the answer in the back of the book. All right. Well, let's do one more example that's even maybe just a little bit fancier. So it's going to take up a decent amount of space. So I'm going to go ahead and erase here. And this example is number 40 in the book. So we have h of x is equal to log base 3 of x times the square root of x minus 1 over 2. So I'll put the brackets there and got to do a lot of work. So the first thing that we want to do, I think, is rewrite this radical as to the 1/2 power since we're working with logs. So h of x is equal to log base 3 of x times x minus 1 to the 1/2 power over 2. So I did that even before going through the simplification process. So I'm just kind of doing one process at a time here. So all we're doing is rewriting to try to get this thing to where it's easy to take the derivative of it. Okay, so, and by the way, I'm so sorry about that. I didn't put the natural log. So we're gonna, I forgot there to go ahead and use the change of base formula. So I'm gonna have the natural log of x times x minus 1 to the 1/2 over 2 over the natural log of 3. Okay, so we've got this 3 here to deal with. Okay, so now I'm going to bring 1 over natural log of 3 out front. And then I'm going to multiply that times the natural log of x times x minus 1 to the 1/2. And you might want to combine all of this a little bit, do more than one operation at a time, but I'm doing this for illustrative purposes here. Okay, now I'm going to use I've got the change of base formula to get it into natural logs. Now I'm going to use the properties of logs to try to get all of this separated out so I can take the derivative. So far, all we're doing is rewriting. So I've got 1 over natural log 3, bracket here, x times x minus 1, that would be the same as addition. We've got multiplication here on top. So that's going to be the natural log of x plus the natural log of x minus 1 to the 1/2. And then what we have on bottom, we subtract. Remember, this is a fraction, so minus the natural log of 2. And I can do one more thing. I can bring this 1/2, this exponent, out front, right? Properties of logs. So 1 over natural log 3 times the natural log of x plus 1/2 times the natural log of x minus 1 minus the natural log of 2. Now you might have combined all of that and gotten all of that here, but I wanted to show you how I got the 1/2 for this first one. Now we can finally take the derivative. So h prime of x, the constant out front, we've got 1 over natural log 3. Now what's the derivative of the natural log of x? It's 1 over x. Plus, we have 1/2, this constant out front. The derivative of natural log of x minus 1 is 1 over x minus 1 times the derivative of x minus 1, which is just 1. And what's the derivative of the natural log of 2? Well, that's just a constant, so the derivative is 0, right? Just a constant, like the derivative of 2 would be 0. So that's going to be 1 over natural log 3 times 1 over x plus 1 over 2 times x minus 1. Now, in my class, you would get almost all the partial credit for getting to here. However, to match the back of the book, they expect you, and maybe whoever your teacher is, expects you to simplify further and make this into one fraction. So let's go ahead and do that. We'd have 1 over the natural log of 3. So to get the common denominator, I'm going to multiply the two denominators together. So that's x times 2 times x minus 1. So that'd be 2x times x minus 1. And then I bring the one on the left up top, so excuse me, the one on bottom right up to the top left. So that'd be 2 times x minus 1 times 1. And then plus, there's a plus there, x times 1. So we do this cross multiplying thing here. And then I'm just going to make that, we have 2x minus 2 plus x over 2x times x minus 1. And then we can improve that a little bit. So we'd have 3x minus 2 on top. And on bottom, 2x times x minus 1. Again, in my class, I would be thrilled if you got to here. And you would get almost all the credit if you got to here, because that's the calculus. The simplification, if you didn't get the simplification right, I would personally only count off 1 point on the problem. So get to here, but if you want to match the back of the book, you got to go through this simplification process and get to here. All right, so let's write down the homework. So the homework is page 354. You want to do 1 through 13 odd. Should do 14b. Then 37, 38, 39. And we did 40, so you can skip that one. 41, 42, and 43. And so give those a try, and then you can watch the solutions video and see if you got them right. All right, that'll do it for this lecture, and I'll talk to you on the next one.